So in a vertical lab, we have equipment that goes to the operator instead of the typical setting where the operator is always going to the equipment. So in an inorganic solid state synthesis setting, we might have some powder dispensing, something for doing synthesis, something for characterization, something for mechanical testing. And we have this typical lab bench where some are on a table, some are just kind of these freestanding modules. And oftentimes we'll see things like mobile manipulators or rails or lots of equipment kind of centered around a single robotic arm for some of these workflows. And in this vertical lab, we put our equipment on a tray that can stay powered. We have this sort of operation bay. We have storage in the front, storage in the back, and this lift or elevator module in the middle. And so we have this powered equipment that can be stored up near the ceiling, running experiments. And when we need to swap out a sample or do some maintenance on a piece of equipment or use it manually, then we can bring it back to the kind of operation bay. This is an example of a vertical lift system, a vertical lift module in use. If we take a look as if we were riding the tray, we see it coming up towards the top. We'll see a little bit of the light coming through the ceiling. It going into position. And then coming back down. And so that's a system we've done some testing on. We're looking at getting one for Brigham Young University. We've done a lot of vibration testing, putting microscopes on here, and overall just kind of vetting this idea. Really looking at utilizing vertical space in an automation-friendly way, not just in a vertical space utilization framework. We have a lot going on with kind of remote control and asynchronous kind of cloud experimentation with things. So here we can see a web app. You can also control this with Python. We have a YouTube live stream going 24/7 and saving all of these 8-hour chunks of videos, sending our commands, getting our data back from these systems. And one of the third kind of key concepts that we look at here is this idea of a frugal twin. So my favorite example of a frugal twin comes from Anis Fisker-Bodker. He went to the Acceleration Consortium. In about 3 months, built a self-driving lab for electrocatalyst discovery with the help of some others within J. Hetrick Simper's group. And he did this for under $5,000, replicated this after the stay. And you can see an example of the sophistication of this workflow here. It's reusing a pipette tip to pick up different tooling. It's adding the metal precursors. We'll see it pick up an electro deposition tool. What's the electrode? Perform the electro deposition, ultrasonically clean it, and continue and carry this out in a loop. So just briefly, one of the kind of more related to this symposium specifically, we have these real world materials discovery tasks that require more than just vanilla optimization. One of the ones we'll be tackling in depth is alloy discovery for structural and aerospace applications, especially 3D printed or additively manufactured alloys. And so you'll end up with, for your own problems, you'll find things that are multitask. So you might have simulations and experiments that you're trying to integrate together. There are always multiple objectives that are at play, a mix of continuous and categorical variables, high dimensionality. Maybe you're dealing with dozens of parameters in a search space, and these linear constraints on your on your composition. The sum of everything has to equal 1. And then sometimes these nonlinear constraints, like these n choose k ones, you might only have 5 active or non-zero kind of non-zero weighted variables out of your 20 different materials that you could choose from. Now, if we take these and we look at single versus multitask and same kind of presence or lack of presence for each of these. On the far left, we have vanilla optimization. This would be the most basic. And if we move to something like a multi-objective and high-dimensional task, we'd start referring to this as advanced Bayesian optimization. Honigumi is a tool that helps you quickly create examples for these minimal working examples for more advanced optimization tasks. So on the left here, we see that we have 21 lines for this vanilla BO problem. We move to something that's multi-objective and high-dimensional, and we jump up to about 62 lines for this. So there's more complexity, changing APIs when we move to this other regime. And this kind of approach pairs well with large language models. So here we have a preprint soon to be published, Honigumi, this interface for accelerating the adoption of Bayesian optimization in the experimental sciences. And I'll close out with a video just showing the tool itself. So here on the main docs page, honigumi.readthedocs.io, we have our kind of vanilla Bayesian optimization with everything on the far left. And we'll get, as we click on the right, and if we just become obnoxious and select all of the right-hand items, we'll see this template dynamically populate in a self-consistent way. So you can actually just copy this, bring it into a Colab notebook or a regular Python script, just install the dependency and run it fully. There's a series of tutorials covering single objective, multi-objective, batch optimization, featureization, multitask, and benchmarking. Lots of great tutorials. A lot of this comes from Andrew Falkowski, excellent individual from Taylor Sparks' group. And there are also a series of conceptual tutorials as well. So these documents around what does it mean to be frequentist versus fully Bayesian when we're talking about Bayesian optimization. This is especially relevant for high-dimensional Bayes opt. So Honigumi is one of the tools I'm most proud of over the course of my study and career and research, and I highly recommend you check that out. And we'll try to push out some great work in the vertical cloud lab at BYU, focusing on alloy discovery and advanced Bayesian optimization methods.